So welcome. Good to see you guys this morning and back on Zoom. And hopefully this will just be a 2-week transition time to let the infection rates decrease. We'll see. I had planned to do a lab today, and that was the goal, is as many times as we get on campus to try to get you to do as much hands-on as we can. So what we're going to do is actually start to have some discussion as if we were going to do the lab. Because one of the big things that College Board tests is, can you think through a given scenario or a certain problem you're trying to solve or a question you're trying to answer? And can you think through how you would create a lab procedure to address that problem or to answer that question? So we're going to basically have a time of discussion with a type of force we've already learned a little bit about, but we'll dig into it just a bit more today. And it was the lab we were going to do. So instead of doing the actual lab, we're going to do a simulation on Gizmo for our Thursday class period. But for today, we're going to talk about what if we were able to do this in person? What are some options? Because the way the questions are often worded on the College Board free response questions is like, you are supposed to find a relationship between this measurement and this measurement. What procedure would you use? What equipment would you use? So it might say, like, part A, list the different kinds of equipment you would use. Part B, bullet point a procedure showing the steps you would take. Part C, describe the data you would collect and why you would collect that data. Part D, talk about how you would analyze that data. How would you graph it? What kind of calculations would you do with the data? And then part E, if this was the data you collected, what is a graph that you could use to create something that would tell you a meaningful information, like a graph where the slope was meaningful, or a graph where the area under the curve was meaningful, something like that. So there's always sometimes more than one, but there's always at least one free response question that's based on lab. And because at least to this point, you really haven't had a chance to do any labs. I mean, even the thing that we did for those that were on campus the other day, it was just more of an activity than a lab. I mean, you didn't really have to think about a procedure, or it was more just a visual hands-on activity. But I want us to practice that skill of thinking through, okay, well, what kind of equipment would I need? And then how would I use the equipment, and what kind of data would I collect using that equipment? And then how would I manipulate that data graphically and mathematically in order to come up with something meaningful? So that's what we're going to do today for part of our lesson. And to help us with that process, we're also going to review Hooke's law, which is about springs and the forces that springs generate. So that's a quick synopsis of what we're going to do today. Let me go ahead and start sharing the agenda screen, since we're talking about it anyway. And also, just to give you this reminder that we do have 2 assignments that are due today, and make sure you're getting those submitted on Axis. And as you submit them, make sure that you are submitting each individual assignment as a single PDF. So they're actually 2 different assignments, just as they were 2 different activities. So for the feelings in an elevator mini lab, whether you did it on campus with the spring scale and the little black weight, or whether you did it with a rubber band and something strapped to the rubber, tied to the rubber band, it doesn't really matter. That's really just a single page document anyway. Hopefully you can scan it in such a way that it stays as one document, and hopefully you can get it to submit as a PDF. That's by far the safest route. So single document, PDF, if at all possible. And then for the elevator video analysis, that actually is, I think, the more in-depth and kind of makes you think, makes you work a little bit harder. Maybe the better of the 2 assignments. The one was more just to give you something hands-on to do for those that could come to campus, and even those that couldn't. But the video analysis is really one that I think challenges you to go a little further. And that one, again, if you can scan that in such a way that all 3 pages are in one document, that would be great. Assignments all semester, remember, are going to be still turned in on Axis, because we are going to, I'm sure we already are having this kind of coming and going on and off campus. And so I'm sure that's going to at least continue for some time. So we'll just stick with the standard of turning them in. And remember that they are not due until 11:59 p.m. Pacific time. So we'll have some work time at the end of the period today. If you have questions on either of those assignments, you'd be welcome to stick around. I'll remind you at that point that you can stick around and ask questions. But today, as I said, we're going to try to review both the TOAGAMRB acronym that we learned way back at the beginning of the semester in August, and then also talk about Hooke's Law, which we learned right before Christmas. Well, not right before Christmas, but before Christmas. And do some brainstorming and heavy work in some breakout groups to see if you can come up with a procedure. And then at the end, the assignment will be another worksheet and some positive physics questions on Hooke's Law. So let's go ahead and review quickly. In the chat, if you remember what the TOAGAMRB acronym stands for, type in the chat what those letters mean. Anybody remember TOAGAMRB? A couple people got it. To obtain a graphical and mathematical relationship between. Good. So several of you starting to remember it or finding it in your notes, one or the other or both. That acronym is not a College Board acronym. That's a Mr. Webb acronym. Actually, I stole it from another teacher, but I stole it from a curriculum, not a single teacher. But the curriculum that's called Scientific Modeling uses this acronym. And the acronym is designed to give you kind of a framework for thinking through graphical and mathematical relationships and how you would discover those in a procedure. So if we had been on campus last semester and if we were on campus today, what I would be doing now is saying, okay, here's your goal. You have to figure out how you can support Hooke's Law using the TOAGAMRB framework. How can you obtain a graphical and mathematical relationship between force and the displacement of a spring to prove that Hooke's Law works? Basically, that would be the assignment. And we would have a little bit of a brainstorm, but instead of doing it in a general session like this, after we've reviewed Hooke's Law, I'm going to put you in breakout groups and have you brainstorm in small groups. What kind of procedure could you design that would help you TOAGAMRB Hooke's Law, basically? Okay, now sometimes in class, the goal would be to TOAGAMRB to develop this relationship before you know anything about it. So it's more of an inquiry discovery kind of an activity where you don't know what the relationship is. You don't know if it's going to be a linear graph or a quadratic graph or an inverse relationship. And so you're just gathering the data to actually discover it. In this case, though, we've already learned Hooke's Law. And my main goal for plugging it in right now is twofold. One, to review forces and to review Hooke's Law specifically as a type of variable force. And then secondly, to give you a chance to practice this whole development of a procedure with a relatively simple relationship. And so we're going to, even though we can't do it hands-on per se, or at least not in person, we're going to still talk it through. So let's review Hooke's Law briefly, and then we'll come back to this TOAGAMRB acronym and apply it. So Hooke's Law is about spring forces, or forces that springs exert. And it's a mathematical relationship. You may remember it's on the AP formula list. And it's a variable force. So when we first started talking about it, the main point of bringing it up was that it's an example of a variable force like air resistance. So if you take a spring that is strong enough to withstand pretty large forces, if you stretch it, it'll eventually reach the point where you can't stretch it any further. It will, at the beginning, not seem that hard to stretch. And then the further you stretch it, the harder it is to continue to stretch it. So the force is not constant, it's variable. The more you extend it, the greater the force it requires to continue to extend it. Same thing with compression. So the more you would compress a spring, the greater the force is required to continue to compress it. So it's a variable force, and that's one of the things we learned when we were studying it initially. Now, Hooke's Law mathematically, we saw it in this form, that the force of a spring is equal to negative k times x. Sometimes you'll see the absolute values around the x, sometimes you won't. The reason the absolute values are there is that it doesn't matter whether we're stretching or compressing the spring. So we could be pulling it apart or pushing it together. The direction doesn't really matter. The function is still the same. So we don't need to know whether it's in the positive or negative direction per se. We just need to know how much was it stretched or compressed depending on whatever we were doing. Now, what does the K value refer to? Who can unmute and remind us that? What's that K value?
It's like the resistance, I guess, kind of. It's the Newton per meter. So I guess force per length stretched.
Good. So it's something that represents the rigidity or the stiffness of the spring itself. It's something that's a constant related to that spring. If we related it to some other thing in force that it's similar to, it would be kind of like the coefficient of friction, how the coefficient of friction is specifically related to what the two surfaces are. So in Hooke's law, that K is a constant specifically related to whatever spring we're using. And so if we change springs, we would change the coefficient or this spring constant. The X is how much the spring either gets stretched or compressed, and it has to be in meters because, like Ethan mentioned, the units for the constant are in newtons per meter. So if we want to figure out what the force is, if the constant has newtons per meter units, the displacement, the stretching or compressing has to be in meters as well. Now, if you think about how big a meter is and how big most springs are, we normally don't measure how much a spring stretches in meters. That would have to be a really large spring for it to stretch a full meter. Most springs we look at would be pretty little. So it might be like a spring in a ballpoint pen, might be a spring on a door to help pull the door closed, might be the spring on the shocks and suspension of a car or truck or motorcycle. So there could be all different kinds, all different strengths, all different rigidities, but generally speaking, none of them are going to compress or stretch by a meter. Okay, so even though they need to be measured in meters, typically, if we're looking at it with a ruler or a meter stick, we're going to be measuring it directly in centimeters and then making sure we convert it to meters. So keep that in mind that you're often given the values in centimeters and have to convert it to meters. Now, the negative sign that's in this equation, if I remember correctly, I don't have my AP formula guide here right with me, but I don't think they put the negative sign on that formula sheet. The negative sign in this case, in this equation, is really more of a conceptual reminder. It's not so much an actual needed mathematical function or mathematical computational value. It's more just to remind us that in springs, it's always a restorative force. So if I pull it apart, the spring is going to try to pull back against me to restore the original shape. If I push it together, it's going to push back against me to try to restore its original shape. So the force that a spring applies always tries to restore its original shape, and that's where that negative comes from. All right, now we talked about graphing out force on the y-axis versus the stretching or compressing elongation displacement of the spring on the x-axis. And Hooke's law, if we look at it mathematically, neither the independent or dependent variables are squared. There's no fraction when we look at the independent and dependent variable. If we're putting f on the dependent y-axis and displacement on the x-independent, we see it's going to be linear. And if we graph out the data, we should see a linear relationship. All right, so your goal in today's brainstorm is to confirm that it would be mathematically and graphically a linear relationship, a directly proportional relationship. Now in lab, you would actually hopefully gather the data and see that it is, but today it's going to be more of a mental exercise. Another thing about the graph and the relationship of Hooke's law in general, if we push just a small bit or pull just a small bit on the spring, it would elongate or compress just a small amount with a small amount of force. And if we push or pull with greater force, then it's going to elongate or compress a greater amount. So you can just see here, small force would make a small displacement, greater force would make a greater displacement. The other thing that we can figure out is if we find the slope of this, what would the units for the slope be if this is our graph? What would the units for the slope be on this graph?
Newtons per meter.
Newtons per meter. And what did we say just a few slides back that newtons per meter unit matches with?
K.
The spring constant, the K value. So when we graph force on the Y and X on the X, displacement on the X, the slope is the spring constant. All right, so that's another thing we discovered when we talked about it the first time. So therefore, if we look at graphs of multiple different springs, a spring with a large spring constant would have a steeper slope, and a spring with a small spring constant, a flimsier, less rigid spring, would have a shallower slope or a smaller slope. So just a couple quick review questions to make sure you're remembering what you need to remember about Hooke's law. If we're looking at these two examples where we've got the blue line kind of representing a blue spring and the green line representing a green spring, which one requires greater force to stretch, blue or green? You can put it in the chat, A or B, or would it be the same? So you can put A, B, or C in the chat. All right. Took a while for my computer to catch up, but now I'm seeing a bunch of A's coming through all at once. So good. The A, blue, has a steeper slope, so therefore it would require a greater amount of force to stretch it. All right, now let's do some mental math. If we have an ideal spring with a spring constant of 25 newtons per meter, what would the force be that's required to stretch it, displace it by 2 meters? So again, just go ahead and calculate this, put your answer in the chat. All right, same thing. Seems like there's a little bit of a delay to come through on my second computer, but I'm seeing a lot of agreement here as they do come through. Whoops. That we get a 50 Newton force. We take the constant 25 newtons per meter times the displacement 2 meters, and notice here that the meters would cancel, so that's why our units are important to think through, and our force is 50 newtons. All right, just two more quick ones to finish our review. An ideal spring requires 3,000 newtons of force to stretch it 5 meters. Determine the spring constant. So go ahead and figure it out. Put it in the chat. All right, we're getting a lot of agreement here as well. If we're solving for K, we need to take the force divided by the displacement. If we have a 3,000 Newton force and a 5 meter displacement, the spring constant would be 600 newtons per meter. All right, very good. And last one. The force of 100 newtons is applied to a spring with a constant of 250 newtons per meter. What is the resulting displacement? Okay, starting to see some consistency coming through here as well. If we're finding the displacement, we're solving for the x. So the x would be the force divided by the constant. So if you have a 100 Newton force divided by a 250 newtons per meter constant, the newtons cancel, and we've got per meters. So whenever you're dividing by something per meters, that means you'd be multiplying by the reciprocal. So the unit does end up being meters, and 100 divided by 250 gives us a 0.4 meter stretch. So about 40 centimeters stretch on this spring. All right, questions about using Hooke's law mathematically, about graphically considering Hooke's law, anything? All right. Fairly straightforward law, and again, a review of what we've talked about before. I changed a couple of the questions slightly, but so hopefully a little bit of freshness to it. All right, now what we're going to do next is to go back to this whole TOAGAMRB, obtaining a graphical and mathematical relationship between. And I'm going to put you in breakout rooms in just a few minutes, and I want you to, in your group, think through if we were in lab and you just had typical experimental equipment, rulers, meter sticks, springs, force meters, ring stands, just, the things you would normally find in a science lab. How could you obtain a graphical and mathematical relationship between the force you exert on a spring and the displacement that that spring experiences? So those are your two variables I'm wanting you to find the relationship between. And your goal in the breakout, give you about 10 minutes, is to come up with a procedure. What would you do if we were in lab and you had the normal equipment? How would you design a procedure? What would you use? What would you measure? How would you measure those things that you want to measure? And then once you've made the measurements, then what would you do with that data to come up with a graphical and mathematical relationship? So you're going to be in groups of 3, I think. Let's see, roughly. Might have one group of 4, it looks like. I haven't done the math exactly, but we'll mostly be groups of 3. And I'd like each person in the group to address something. And you can decide in your group how you're going to divide it up. You could divide it up amongst these 3 questions. You talk about what we measure, you talk about how you measure, you talk about what we would do with the data. Or you could break it down into the TOAGAMRB. Say, okay, you talk about the procedure, I'll talk about the graphical relationship, I'll talk about the mathematical relationship. Okay, so however you want to divide it up. You can even divide it up another way that I haven't mentioned. But I'm going to give you about 10 minutes. And again, you're trying to find the graphical and mathematical relationship between force and displacement with an experimental procedure. When you come back, each group will share their ideas with the class, what their procedure would be, what they would measure, how they would measure it, and then what would they do with that data to actually come up with the graphical and mathematical relationships. Any questions about the goal for this breakout? All right. So a couple of the groups will have 4. So you'll have to divide it 4 ways in terms of your explanation. All right, off you go. Sorry, I was muted there. I think everybody's back from the breakout group, and let's have group 1. So we've got Jack, Johnny, Rocky, and Sally. Talk to us about what you guys came up with.
So what we would measure is the force in newtons that is exerted onto the spring scale, and then we'd measure how that force affects the displacement in meters.
And how you would measure that. So number 2, you would use a spring scale and attach the hook to one end of the spring and pull it to until a certain number of newtons is derived, and then use a meter stick or a ruler off to the side and measure how far the spring traveled from one end to the other.
And then for what would we do with the data we collected, we can plot it on a graph with the meters on the x-axis and the force on the y-axis, and just use the data we collected. And then for the slope,
yeah, slope would just be, as we said, newtons over meters, and I think that's everything.
Okay, very nice. So a couple reminders about lab and College Board, kind of connecting the two. You guys did a great job, by the way. the procedure would work wonderfully, and your outcomes would be great too, hopefully. The goals would be. So the other thing I would say, though, just more generally speaking, I mentioned this earlier, but I want to remind you again, the TOAGAMRB model is something that you would want to think through, helping you know how to answer the question. It's not an acronym College Board uses. And then there's another little memory device that I talked about quite a bit at the beginning of the year that would be important for you to remember. It's also a little memory device that College Board doesn't use, but it helps you remember an important thing about doing any experiment in terms of making sure you have enough data. Does anybody from that first group remember what rule I'm referring to that helps us know how much data we should collect?
The 8x10 rule.
Yeah, can you refresh our memory? What is that rule talking about? And it doesn't have to be Johnny, it can be anybody.
It's that you have to have at least 8 data points, and that the first one and the last one has to be 10 times as big.
Excellent. Yeah. So again, College Board doesn't use like the 8x10 rule phrasing, but so you wouldn't say in your essay, use the 8x10 rule, because the grader may or may not have any idea what you mean by that. But it would be important for you to say, because typically one of the points in the essay, and most often they ask you to write an essay explaining some of this. So one of the points typically is, did they say that they were going to collect a certain amount of data that would be sufficient? In other words, not just 1 or 2 data points. So if you go by the 8x10 rule and say, we would collect at least 8 data points and make sure that our largest measure for the independent variable is at least 10 times larger than the smallest measurement of the independent variable. If you covered the 8x10 rule in your essay, then you would have earned that point that's often part of the rubric. So we didn't review that today, but after hearing your procedure, it sounded like a great procedure. I would say the one thing you probably want to add that the rubric normally asks for is that you do have sufficient data, and that using that 8x10 rule reminder can help you make sure you include that. So excellent job, group 1. Group 2, Aiden, Andy, Ethan, and Kyle. What did you guys come up with?
Our setup is very similar to theirs, pretty much the same. It's where we'd have like a spring against a wall or anchored to something where it can keep it still, and then attach the spring scale to it and have a ruler alongside it to see the measurement and how it corresponds with the force of the spring.
Yeah, and we'd be measuring like the force required, and like for us, we talked about like the independent variable, and we'd set certain distances and then stretch it, and then to see how much force would be exerted.
And then for the graph, we'd basically have distance on the x-axis and then force on the y-axis. So it's pretty easy to do.
And then our mathematical model, we would derive from the graphical model by because we'd see that it's linear, so we'd take y equals mx plus b, and then put in 2 points and do the algebra to find the mathematical model. And we'd have 8 points separated by power 10 to follow the 8x10 rule.
Good. Yeah, very nice. And then some of the details you gave there were really good. Not that they would be necessary, but I liked that, you said anchoring it to the wall or something. So those little details, it gives the grader, because I've been a grader, so it gives the grader confidence that you know what you're talking about. And if you didn't say we anchored it to the wall, they're not going to take off a point for that, as long as what you wrote was clear. But adding those little details without adding too much. You don't want to write this big flowery essay, because that also will turn off the grader, honestly. If you have a bunch of stuff in there that's pointless and you're just obviously trying to pad your essay, that can sometimes turn the grader off, and they're human. So, if they're frustrated by you adding a bunch of stuff that's irrelevant, then there is sometimes even in the rubric a point that says you can deduct a point if you feel like they're adding irrelevant information, or if anything they say is wrong, you can deduct a point. So the more you add that's irrelevant, if you make one slight mistake in that, you could lose a point. So you want to kind of walk that fine line of adding those details, but not making it big and wordy and trying to say too much. So you want to, it's a balancing act on that regard. But I like what Aiden said and what you guys discussed about identifying, oh, this would be our independent variable and this would be our dependent variable. Sometimes, not often, but sometimes that is actually part of the rubric. And so it's always a really good thing to include what you're considering each of those. Another thing that you could include, and for this one probably wouldn't be as critical, but for other experiments it might be, is what things were you trying to control? So things like we use the same spring scale every time, or we use the same spring every time. Some things like that where you're trying to make sure you're controlling certain variables. So nice, both groups did an excellent job. And last group, we've got Cade, Evan, and Nat.
So we would measure the spring by, like the other group said, putting it alongside a ruler and seeing how far the spring moves when you pull it back. But another way is we could use one of those springs that's contained within those measuring boxes, which we used last class, since they sort of have that side-by-side ruler that you can measure the displacement.
Mm-hmm. Yeah, good. Evan or Nat?
It's Evan's turn.
Oh, okay.
Well, I was just gonna, my part was to say that we were gonna measure the displacement and the force using like measured weight things. So we would like calculate the weight force of an object and then put that at the bottom of the string. And yeah.
So like using those black weights like we did on that last little hands-on activity?
Yeah.
Yeah. Okay, good.
And then after we collect multiple samples of these data points, we would plot them on a graph and draw a line through like the points that most, like a line that hits the most points. And then we would use those points and find the slope on that line and then plug it into the F-spring formula equation.
Good. Good. Yeah, so I like the little detail you added there of finding that best fit line. That's a nice little addition to, probably not something you would lose points for if you didn't have, but another one of those small details that would give the greater confidence that you know what you're talking about. Good. And actually the way that you guys described it with the point Evan made of hanging weights on the spring, that's actually the way we typically do it when we do it on campus, when we do it in class, is we get a ring stand. If you've had chemistry, you know what a ring stand is. It's got like a base and then a bar that goes up, and you can attach different kind of clamps to it. And we just put a clamp on it and then hang a spring from the clamp. And then you just put weights on the bottom and you put a meter stick beside it. So you put a 50-gram weight, see how much that stretches it, put a 100-gram weight, see how much that stretches it. And you just keep putting different weights on there and using the meter stick, see how much it stretches each time. The first two groups talked about actually applying a force and measuring with a spring scale, which is also equally valid and equally functional. Both procedures would be great. The only other thing I would add that you could consider, not better or worse, just another alternate method, would be instead of using the spring scale, and one thing that I don't think we've really talked about much, but you may have seen before, and I may have mentioned, I don't recall, is using a force sensor. So there's actually, almost all labs would have some kind of a force sensor where you could hook that to one end of the spring and pull it, kind of like the first two groups talked about, and the sensor would tell you digitally how much force you're applying to stretch the spring a certain distance. So that would be another piece of equipment that you could include in this or any lab that required forces. A force sensor is generally considered typical physics classroom equipment. All right, so not that you would need to use it, but if that would ever be helpful, I'd like you to know about that. And if we can't get back onto campus much, then I'm probably, one of the things I'd like to start doing is setting up some labs and just doing a real brief overview and showing you some of the equipment in action. If you can't actually use it in person, the next best thing is to at least see it in action. So that's something I'm going to start trying to do this semester, seeing as how we're going to at least be somewhat limited to being on campus, I think. Good, nicely done. All three groups came up with really good solutions, really good strategies. and we had a chance to review quite a bit there as well. Any questions from any of the groups or any of you individually about the Hooke's law, designing a procedure, thinking about TOAGAMRB, 8x10 rule, any of that stuff? All right, well, very nicely done. The last thing I want to do is just explain the assignment. So let me go back to the screen here. So the assignment is going to be what's called the Hooke's, or what I'm calling the Hooke's Law worksheet. When you open it up, the title at the top of the page actually says force exerted by a spring. And I'm going to show you on Axis a couple of things just to make sure you know where to find it and how to submit it. Since it's our first one for this semester, with this combo, because it's got a new thing that we're going to do, I want to kind of show you a couple things. So let me go to our browser here and go to Axis. So the first part of this is you should probably already know, but you'll go to topics, and just to make sure you know where to find it, it is in Unit 6. So we're reviewing Unit 6 material. So you go to Unit 6, click on Unbalanced Force Model, Unit 6, and then there it is, Hooke's Law Worksheet, PDF in document form. All right, so that's probably pretty straightforward. Now, I want to show you what the document looks like, though, because there's something new on here that we haven't done before. Well, at least not in this way. So once you open it up, this is the PDF form of it. You'll see that the title on the worksheet itself is Force Exerted by a Spring. So even though I've called it Hooke's Law on Axis, it's Force Exerted by a Spring is the title on the page. And it gives you Hooke's Law right here at the top. And I believe, if I remember correctly, this might be the way it is on the AP formula list, where both the force and the displacement are in absolute value markers, and there's no negative sign. I think that's how College Board writes it, because we don't really care the direction of the force or the direction of the spring, because whether we're stretching it or compressing it, it's the same relationship. You can see these first 4 questions are basically just like what we practiced in class today, so they should be pretty straightforward. But at the bottom of the page, well, on the second page, let me mention this first, you can see the answers, so you can check your work and make sure you're getting the correct answers. You can see I've made a note. I used 9.8 meters per second squared for G when I needed to use that. And then I've given you an answer and then the rounded answer considering sig fig rules. So you can check all of that. But you'll notice at the bottom of the first page here, this part. This is the new part. Not that we've never used the Positive Physics website, but we've never combined it as part of a worksheet. So it says complete the work section for the Hooke's Law skill in Unit 17, Springs and Oscillations, on the Positive Physics website. Submit a screenshot of your result. And so if you open this up as a Word document, you can just take a screenshot and then just paste it right into your Word document. And I'd like you to have it all in one place when you submit it. Okay, it's basically you're doing 4 questions on this worksheet and then 2 additional questions on the Positive Physics website. So let's go to the Positive Physics website briefly and make sure you know how to do that. So once you go to the Positive Physics website, you'll log in. It should be your last name followed by your first name. So I'll do my fake student here, Bird Larry. And it should take you to Unit 17 directly. Now, I do want to make sure you understand you are only doing the work section, not the assessment, and you are only doing the Hooke's Law skill. Okay, so you're not doing review, inquiry, all these other things. We haven't learned a lot of those other things yet. So you're just doing this Hooke's Law skill. There is a video to help you if you need it. And if you click on this, you'll see over to the side here, there's just 2 questions. So when you click on it, it's going to open up the 2 questions. You can see one of the questions is oriented with the springs vertically, and then the second question has them oriented horizontally. And it's just using the Positive Physics format to evaluate Hooke's Law. 2 more questions. So you don't need to do the work on your worksheet. You can just do this and then take a screenshot to show me you've completed it. You can do corrections because it's in the worksheet, so you don't have to finalize it or anything like that. And you can either take a screenshot of this top corner, because you can see it shows your name and it shows your percentages, or you can go back to the dashboard and take a screenshot. Again, the name is kind of up here in this corner, so make sure you're showing the name, and then it needs to show at least this Hooke's Law percentage down here. All right, now you can go back and correct them, and as long as you correct them, your completion percentage should be 100%, and that'll be your score. Okay, so as long as you correct them, you should get 100%. And just add that screenshot to your worksheet somehow. Now, if you look at it on the assignments, just a refresher here, you'll see it as Hooke's Law worksheet. When you click on it, gives you some directions. Complete the Hooke's Law worksheet showing all your work. So just having the answers isn't good. I've given you the answers, right? So you need to show me your work. Number 2, complete the work section of Unit 17, Springs and Oscillations for Hooke's Law on the Positive Physics website. Submit a single PDF for your worksheet and a copy of the screenshot of your Positive Physics results on that PDF document and put it on Axis. All right, so that's your steps, and then I will check it out here. Any questions about what to do?
Do you have a easy procedure of getting the screenshot into the PDF? Because I know I usually just use Genius Scan and take pictures with my phone.
Mm-hmm. Are you planning on just printing it and doing it that way?
Yeah.
Okay. Can you, with your Genius Scan, I'm not sure about Genius Scan, I haven't used that one in a while. Can you take pictures with that? It's what you're taking pictures of the paper, right? Just take a picture of the screen of the page.
Okay, I'll do that, and I'll try to make it
that
as
should work.
good as possible.
That's how it works, right? You take a picture of the paper.
Yeah.
So then just take a picture of the screen as your last page.
Okay, sounds good.
Yeah,
Thank you.
Genius Scan and other ones like it. I use a different one. I forget the name of it, but I think they kind of all work the same. That's handy because you can just do your pictures of your paper and then do a picture of your screen, and it just puts it all in one document. On the worksheet, you don't need to scan the answers side, just the side that shows your work is sufficient. Any other questions? All right, so let me go ahead and stop sharing here. We got 11:25, right? Is that our normal dismissal time? Yeah. So you got about a half an hour almost, just a little under a half an hour to work on that. I'll keep the Zoom running until 11:25 in case any of you have questions. If you have questions immediately, you're welcome to stick around and ask them. If you don't have any questions, you can be dismissed and just work on your assignment, but I'll keep the Zoom running in case you want to come back and ask questions later. So if you don't have any questions, I'll see you next time. If you do, stick around. I'll be here.
Thanks, Mr. Webb.
You're welcome.
Thank you.
Thank you.
Thank you.